Next presentation comes from Poland, and by Professor Jaroslav Cleavage, and he put the question: are the mechanical speed parameters sufficient to predict uniquely behavior due to ductile or cleavage mechanisms? And we hope for an answer.
Thank you, Mr. Chairman. Ladies and gentlemen, I'd like to present part of our program concerning initiation of the fracture. So we would like to describe this event using standard well-known parameters like stress reactivity, loader parameter, plastic strain, or opening stresses. At first we need some experiments, so we use steel, as you can see, F355 subjected to 3 heat treatments, and from these 3 in fact materials we cut 5 different specimens. You can see 4 geometries because this at the bottom was cut into versions with notch root 0.4 and 1 millimeter. And these specimens were subjected to loading in different temperatures. Here I present results from -50, -20 and +20 degrees Celsius. So as you can see, we obtain very different mechanism of fracture from cleavage to ductile, and from our point of view, these mechanisms depend on material, temperature and shape of specimen. Our big questions were where and when fracture begins. So to answer when, we use load displacement curves and we watch them, and since we have no such things like pop-ins or sudden load drops, we assume that this process of fracture begins at the end of loading stage. And to find these places where it begins, in the case of a cleavage fracture, we try to use river patterns, and it was successful. However, we have problem with ductile mechanism, because initially we wanted to use shape and size of voids. However, even under microscope, we are unable to find a place where we are sure that this process begins. So that's why we use the Ritchie-Rice formula for spherical void, and we slightly change it, and this equation on the right very roughly describe increase of void. It was for us enough. And now some results. These results come from room temperature. As you can see, there are 2 specimens, CO4 and C1. These are these round specimens, the geometry you can see on the right. As you can see, in the center of the specimen, we have quite good level of plastic strain, if both case, accompanied by high stress reactivity. However, we can't say from these pictures when fracture begins. So we use this our working hypothesis, and as you can see, our function shows that for the CO4 specimen, fracture begins close to the notch, while for the C1 specimen, this fracture begins at the center of the specimen. And I confirmed it with numerical analysis because I use abacus, I use user-defined material and a model proposed by Wierzbicki, and in fact, this specimen broke that way that CO4 start at notch and C1 start at the middle of the specimen. Second specimen is very specific from this room temperature. As you can see, this is specimen PR. This is flat specimen with these rounded notches. And our function shows that fracture begins on the surface of the specimen at point C. This is just in the middle of the specimen. What is characteristic here? It is a low level of loader parameter. On the next slide, you can see 2 pictures, fractographic pictures from the point C. This point is inside, in the middle of this specimen, in this cross section. So, low level of loader parameter is characteristic for shear. So here you can see results pictures from -20 and -50. As you can see, we don't have a clear ductile mechanism, but mixture of ductile mechanism and dislocation signal. So now let's move to cleavage. We drop the temperature, expecting that we get the cleavage fracture. However, two specimens do not want break due to cleavage. Specimens C1 and PR do not break at this range of temperature due to cleavage. They did at -80, -100, however not at least up to -50. So here we have CO4 specimens. As you can see, external area failed due to cleavage, and this core zone still broke due to ductile mechanism. Next specimen, PM. This is flat specimen with kind of side grooves on the surface. This specimen also show traces of cleavage, so we have two zones in the shape of W, which broke due to cleavage, and they were separated by area of ductile fracture. So here we have two pictures. This from the inside of the zone of cleavage shows clearly typical cleavage surface. However, close to these edges, we found mixture of two mechanisms. As you can see here, we have cleavage with voids. So cleavage we want to explain using Ricci-Price hypothesis, which says that cleavage initiates when opening stresses exceed critical area on sufficiently large, critical level on sufficiently large area. So here we have distribution of opening stresses at critical moment for these four specimens and normalizes distance from the specimen center. And we thought that if C1 do not break due to ductile and CO4 and PN did fail due to cleavage, so we should try to find this critical level in the area where these two later specimens have the highest opening stresses. This area is marked by these two vertical lines. And comparing results for PN specimen with experimental observation with refractography, we find a place where cleavage, according to us, started. It was about 0.72 at this normalized distance from the center. For PN specimen, formally it was 6.6 millimeter, and we assume that this stress level is equal 1,240 megapascal. And the same level for CO4 specimen was found slightly later at normalized distance, about 0.86, which physically was only 1 millimeter and 29. So the problem was that watching these results, new question appears. First, was why we do not observe many traces of ductile mechanism at cleavage surfaces, even though this cleavage initiate at the last stage of loading process. And from the other hand, we can see any traces of cleavage in the area dominated by ductile mechanism, even though the level of the stresses shows that they should appear some kind of cleavage. So, to answer these questions, we observe history of interesting for us parameters, and at least we try to answer this second question. Because as you can see here, this is history of changes parameters for PN specimen, and what is for us interesting here, as you can see, plastic strains increase gradually with loading, and they are from very beginning accompanied by high stress reactivity. Of course, after step 12 here, between 13 or 14 of total 70, they were conditioned to develop cleavage. However, we find nothing in this area. So, second specimen, CO4, as you can see, again, plastic strain increased gradually, and they are from very beginning, at least at the central part of this specimen, accompanied by high reaxiality. It's good environment to develop voids. They easily grow. So we thought that we can find cleavage in the area dominated by ductile just because these voids grow gradually, and when we met conditions for developing cleavage, there is no place for cleavage. The whole critical area is full of limbus or other things connected with ductile mechanism. And as far as this first question is concerned, that is why we do not see any ductile on the surface when cleavage is dominating the mechanism. Here we have this, our working hypothesis, the distribution of this function at final stage. And here we have this black continuous line is for PN specimen. Everything from this yellow spot on the left failed due to ductile mechanism. However, on the right it depends, and this is a situation for PN specimen where this function goes down and, well, there is no growing points, so we have cleavage, that's okay. For C1 specimen, this is red dashed line, this function did not drop much, so we can say it is almost constant, so the whole surface failed due to ductile. However, the whole business broke this CO4 because for her this black dashed line goes up. So we should have here ductile mechanism, and we have cleavage, unfortunately. So we think about that up to beginning of holidays this year, and our last guessing is that similarly as in the case of ductile mechanism where critical strength depends on parameters of mechanical fields, critical stress for cleavage mechanism also are function of mechanical parameters, describing mechanical fields. We choose, observing the results, plastic strain and loaded parameters, and here you can see two limiting surfaces. One is upper, which was created using a point that fell into cleavage, and this lower is created using points on specimens that failed due to ductile. So if this area, this surface of critical stress lies between them, it might happen that our processes of cleavage begin more earlier than we thought, so the cleavage appears before oils start to grow. And that is our last conclusion for now. We will see. We still work on this material, so we will see what will happen next. Thank you for your attention.
So you said time again. You wanted to discuss immediately. Other question now? This call.
That's a nice presentation. And my question is just, I can maybe I can understand the drop of the critical stress with when the plastic deformation is high, because of some damage that is caused by dislocations and everything. So the critical stress goes down. That's a little bit. Problem for me makes the first part of the curve, to the maximum. Why this goes up? That's something which I have.
Maybe I say how we create these surfaces. We just have several points for different specimens, different geometries. These geometries were chosen in such a way to have wide range of changes of loaded parameter and reaxiality. So we have in fact several points in the corners of our area. And some specimens break due to cleavage, some break due to the ductile. So we get these points which were failed due to cleavage and try to draw a surface. So we get such shape. Okay, but as you can see, this local parameter do not influence much. I thought that stretch axiality will do something, but rather not.